Hi everyone, this is Jay from Interview Query, and I'm here with Dan again for part two of our machine learning system design mock interview course. And so today we are talking about recommendation systems again. This time we're focusing on a different problem statement and going over just how we would build such a system and implement a lot of the machine learning in practice. And so today the problem statement that we have to tackle is on Spotify. And so this question is asked by Spotify in machine learning interviews. And essentially it is, how would you build a machine learning system to generate Spotify's Discover Weekly playlist? Dan, I guess how would you begin to tackle this question?
Yeah, so I have looked into this a bit, and similar to the YouTube recommendation system, the first thing I would mention is collaborative filtering. And one thing I like about collaborative filtering is that it's infinitely extensible because it is largely domain specific. So you can take research in one topic and tweak it to match your needs at whatever environment you're applying it to. For example, YouTube videos or Spotify songs,
Mhm.
and you can tweak parameters in order to get more accurate results. So for the context of, say, Spotify's Discover Weekly, we have the context of the songs that a Spotify user likes or doesn't like, and we have the context of users over all of Spotify's 100 million plus subscribers. So looking into the question, the first thing that was a little hitch in the road was that on YouTube you have things like did you thumbs up the video or did you thumbs down it? Or you have more explicit of a rating system than you do on Spotify. There's no really thumbs up, thumbs down on Spotify. It's just, did you listen to the song? How many times did you listen to it? Did you skip through? Which is similar to YouTube, but it's going to be a little bit different of a problem. So you could use things like how long have you spent listening to the song, or how many times have you listened to the song, or how many times have you skipped this song. But it turns out something that is probably the most valuable descriptor of what other songs you might like. It goes back to binary of have you listened to this song before. And it's interesting that that's what the results show, but indeed that's what I'm finding on online research. So if we start with the corpus of, okay, we have 100 million users and however many, 300 million songs, and each user has either listened to a song or not listened to a song, or we'll even throw in skipped a song in order to get -1 for skipped a song, 0 for not having interacted with the song, and 1 for having listened to the song. And now we have a matrix. We can even use a sparse matrix for performance benefits because most users haven't interacted with most songs. And then boom, we have uh, a an origin for our collaborative filtering to do item item, song to song, or user to user collaborative filtering.
Gotcha.
And then you
So,
can
so essentially, I guess with this you basically outlined like how the training set would look like, right? Given the fact that
exactly.
you have the skips, the likes potentially on some of the playlists, and like the have you listened to it before? I guess does it
Mhm.
matter how the song kind of like was first generated for the user to begin with? Like if it was a just a radio playlist versus
Mhm.
a user like specifically selecting the song and like searching it up on like the search bar.
I think I'm going to get into more of that when we move away from collaborative filtering as part of this.
Okay.
Namely in the deep neural networks, you're going to have a lot more features that you can apply to this. But I think it's a lot simpler to imagine the collaborative filtering problem as a sparse matrix of -1s, 1s, and 0s.
Okay. Gotcha. Cool.
Mhm. And so it turns out, have you listened to a song is a pretty complete proxy for how many times have you listened to a song, and it improves performance significantly, and you get comparable results. So you can plug that in to get suggestions for will this new user appreciate this new song, or a new suggestion for you as generated into your Discover Weekly. But the best way to do that is probably not by performing deep learning on this entire corpus of users and songs. So what you can do is you can map these users and songs into into a lower dimension matrix, and then a lower dimension vector for each user and a lower dimension vector for each song. And then you can, similar to the YouTube algorithm, you can map it onto on the same space. And then you can do k nearest neighbor in order to select users that are similar to, or songs that are similar to your tastes. And now we have a way to generate an MVP for at least this arm of a recommendation system for Spotify's Discover Weekly.
Awesome. Okay. And so for this whole system, for this MVP, I guess where would we take it from there? Would we start rolling it out and just testing it to see how it would work? How would we begin to retrain this model? Would it be offline in terms of we just compute these, every single week? Or are we doing continual computations basically every second, every single day based on the user's likes and dislikes? I guess how would the rest of the system kind of be built? And then how would we also scale this out for the millions of users that are using Spotify?
Yeah, so as an MVP, I would probably leave it as is with just a collaborative filtering model. And then I would probably do batching in order to say, hey, because the Discover Weekly playlist launches every Monday, I would probably perform incremental updates to my model as users listen to new songs that they haven't heard before. The benefit is that users tend to listen to a similar corpus of songs that they already have listened to, so the model wouldn't be so write heavy. And then perhaps generate
write heavy.
Yeah. So if we were to do the alternative and say record the number of times a user has listened to a song, then on every single time a user listened to a song, we would have to update this model. And that would be very write heavy. We're doing lots of writes continuously, about as many writes as we have reads. But if we just say, okay, has this user ever listened to a song? And we change it to a 1, well, if the user is re-listening to a song more than once, then we only have that initial write. And every time they hear it again, we don't need to write to the model again. So it becomes much less write heavy, which is, we generally would prefer a less write heavy model because it'll be more performant. Writing is usually harder than reading.
Yep. Gotcha. Okay.
So I would do batch updates to say, hey, perhaps every Saturday, begin generating Monday's upcoming playlists for every user across the board, or maybe a sample set of users as we're building out our MVP before we're even close to ready for our 100 million users. And then we could see the errors as they go through. They could be batched, they could be in one place, they could be regenerated on demand. But as we build this out and expand more users into our system, I'm imagining that our batch script would be more susceptible to issues. If one of our 100 million users, or however many people are onboarded already, causes an error, if it's not handled properly, it could cause the whole thing to crash. Which is why I might lean towards a more final solution of a queue-based system. Let's say we could keep a running tracker of every time user updates, hey, I've listened to this new song, or there's this new song and I've skipped it. Now there's an update to a model. Insert their row, let's say, into a queue to say, hey, this thing changed. At some point, process it and update your results to Discover Weekly. Then another queue reader could handle that message and handle only this one user updating their tastes to the model, and then you could regenerate for them that particular user's Discover Weekly. So there's constantly a living Discover Weekly for each user. And I don't work at Spotify, so I can't verify, but I suspect they might use something like that in its current iteration because, of course, Discover Weekly is supposed to discover new songs for you, things you haven't heard. And as a heavy user of Discover Weekly, I find myself being recommended the same songs multiple times. So I'm suspecting it uses a resilient model for my own user preferences. And then as I listen to new things, yes, it does update, but it still might recommend those old songs that it already recommended to me. So this ties into what you mentioned earlier. Does it matter where it comes from? I wonder if I stumbled upon this song more organically rather than by Discover Weekly, it might not recommend it to me in the Discover Weekly playlist. But if Discover Weekly was a thing to recommend it to me, it might not feed back and say, hey, don't recommend this anymore.
Gotcha.
That's just a suspicion.
Okay. Yeah, that makes sense. I guess if we were to hypothetically reinvent Discover Weekly from the ground up, um, we would want it to essentially, like, the goal is to, I guess, come back to it, is to basically encourage our listeners to continue to use Spotify, right? Like, I guess Spotify's
Hmm.
general goal is for us to like listen to as many songs as possible,
Hmm.
and over a longer period of time, given that it is a subscription based model, right? In which
Yeah.
that if we utilize and we listen to Spotify only, then they're happy with that. Just kind of like if people that are watching TV only use Netflix solely as their channel, then Netflix is completely happy with that kind of like optimal user at that point. And so,
Yeah.
cool. Now that we have this kind of MVP model with the queue-based system for handling errors and also generating batch updates for Discover Weekly, how could we potentially improve upon this model? Given that this is the first iteration, how would we maybe like test to see how well it's doing, even and even like just knowing that we might need to update it or make it better. Is there any kind of like additional metrics or things that we need to note of to make that decision? Given that I'm sure it's like a huge project, and
Hmm.
a product manager or executive kind of needs to know like what the cost is of updating it versus the cost of just letting it run and being happy with like this current version of the Discover Weekly generator.
Yeah, and I'm really glad you mentioned that in this context because I feel like it's easy to lose sight of a bottom line goal in order to generate the best model possible.
Hmm.
Because we have to align on a goal. Is the best model to build a playlist that will be most aligned to a user's likes, or is the bottom line goal to generate a playlist that will get users to spend more time on Spotify?
Hmm.
So, uh, with those things in perspective, I think we could use that second bottom line goal of getting more users to spend more time on Spotify as a metric in order to determine success of this thing. And we could use that by counting the number of users that engage with Discover Weekly or the number of users that listen to the Discover Weekly playlist in its entirety. I'm definitely one of those personally,
Hmm.
and things like that. And we could also measure the negative engagement of number of users that try Discover Weekly and then go away from it and don't come back, or maybe number of users that try Discover Weekly and then come back next week. Maybe I didn't like this week's Discover Weekly playlist, but maybe next week I'll give it another chance.
All
And I
right.
think it's important when coming up with models and not only iterating, but coming up with the MVP in the first place, to come up with a hypothesis before you build this and say, I suspect 5% of users will engage with their Discover Weekly, and I expect 1% of those to listen to the entire thing as the entire playlist from start to finish. And then you could measure the results after the fact and determine whether you were correct or not in your assumptions and what you might need to tweak. And that's another reason I like building this collaborative filtering model before moving on as an MVP, before moving on to a deep learning neural network side of things, because I think a convolutional neural network or a neural network in general would benefit from having biases more explicit, and those might come about during testing of an MVP. If your hypotheses are wrong or your assumptions about your users' engagement don't necessarily meet the goal you're trying to approach, it's better to find out those things sooner rather than later, and then maybe pay more attention to particular features when generating them in your neural network, when generating them to put into your neural network, and maybe pay less attention to others if they don't align with uh, the results of your experiments during your MVP.
Okay. Yeah, that makes a lot of sense because I think, if you start out with the black box approach at the very beginning, then you don't know how to
Yeah.
tweak, right, for what your actual goal is, right? Because we could, ostensibly do really well in terms of a small subset of users just listening to the whole playlist, right? But then not account for, like, let's say 99% of the other users that suddenly don't like their Discover Weekly and then never come back to it. And then churn off
Yeah.
of Spotify's platform, right? And so if our goal is to maximize the largest amount of users that use Discovery Weekly at least once, and we find that this model does not do the best, the black box one, then we have no idea how to like unpack that and then learn anything from it. And so that's a great kind of like added kind of consideration there, I think.
Mm-hmm.
Cool.
Yeah.
So I guess for this next level of, I guess, past the MVP, we understand what product goals we have. We understand what kind of metric we need to optimize for. Then how do we start selecting this next model for the second version? And you mentioned like the neural network. Exactly how do we like decide to choose upon the neural network, and how do we go about figuring out which kind of model is the best for this scenario?
Yeah. So in general, I love doing ensemble models in order to receive an output from model A and an output from model B and an output from model C, and combine them with various weights in order to generate a final product.
Okay.
And in order to answer your question, how do I generate content in order to put into, excuse me, my second model, model B of a neural network, I'm going to sidestep a little bit and talk about how Spotify Radio was generated, which is similar, but the concept is rather than generating a playlist for a user, Spotify Radio generates a playlist for a song. So you can put in a seed, an initial song, and it'll generate a never-ending playlist for you based on that song.
Okay.
And so some stuff that came about that I was surprised that is as effective as it is for generating these radio playlists, and which will later apply to the neural network to build a Discover Weekly playlist, is that it uses playlist of user-created playlists, and it says, hey, was this song in a playlist as this other song very frequently? If so, we don't even have to read the data about the song itself, about the makeup of the song. We can just say, hey, this song is with this playlist often. Call that a user, call that collaborative filtering. So now we can combine these two songs and say, hey, if you suggest one, it might be likely to suggest the other as well. Usually this is pretty good, but I do find that sometimes you'll get surprising results. I know I go to a lot of concerts and I record the set list they play. And at a Paramore concert, they did a cover of Drake's Passion Fruit. And so in my playlist of that concert, you see Paramore next to Drake, which is probably not a thing Spotify wants to do on their Spotify Radio because they don't necessarily sound so similar. But it would be boosted in this collaborative filtering model. So that's another point to why you might want to use an ensemble to generate output like this, because your collaborative filtering model might score that high because it appears on a number of playlists next to each other. But your neural network probably will not, because the songs just don't have the same style. They don't really sound the same.
Yeah, that's true. That makes sense. I think a neural network could also potentially correlate those two for some reason with its like kind of hidden weights, right? Because it just has so much training data in that it understands maybe some weird orthogonal correlation with those two types of music. I'm not entirely sure how that works, but I do know that it's based off of the existing kind of like, because music in itself is so non-structured, that kind of association can exist, right? I don't know if that might be a little off tangent there, but still.
Absolutely. And it's important to at least be aware of them, whether you want to boost those signals or account for them by reducing bias on that vector. So when you're using playlists as a generation for this training data model, it turns out you can use a lot of NLP models, natural language processing, for perhaps predict ahead. If you consider each playlist as a document and each song is comparable to a word in a natural language processor,
Gotcha.
so it could do good predict forward, or it could do cohesiveness of a single document, or similarity between two documents to each other. So it's an interesting overlap that I might not have expected. So now pivoting towards answering your original question of how would I apply this to Discover Weekly, is so, in my opinion, analyzing the contents of just an MP3 file of a song is a little bit daunting. So I first wanted to brainstorm the things that, okay, what metadata might we have about a song that we can provide as features to this neural network in order to generate a Discover Weekly playlist. So we have actually quite a bit of metadata about the songs. We know the artist who recorded it. We know the album it was on, of course. We know when the song came out. We know what country it came out. We know the recording studio. And these might not be things that, yes, it will associate these things are similar. So if it's the same recording studio, perhaps it might be the same implicit genre. Or if it came out in a similar year, if this was, a hidden track from the 70s that was just released today, and we want to catalog it, well, we might catalog it associated with the metadata of other songs that were hidden tracks from the 70s per se. Another thing that I learned Spotify does is they scrape articles about music articles written about these songs. They do text analysis on these articles, and they compare them with the other songs that were mentioned or the adjectives used when describing these songs or albums. So there's an entire corpus of, highly iterated on basically information on this. We have a lot of corpus of existing work, a lot of research papers on NLP analysis that we could use for this problem. So this model B could completely ignore collaborative filtering. It can completely ignore the makeup of the song, the actual data in that MP3, and just use the metadata. What are people writing about it? When did the song come out? And who wrote it? And that'll provide at least a small amount of weight or some signal into what it might suggest. And we could tune these weights in order to say, hey, let's boost model B and see how it affects our bottom line, or reduce model B and see how it affects our bottom line.
Gotcha. And it seems like this would be especially useful for like the cold start problem, right? If no one's listened to this song before at all, then we have no idea what kind of users might have liked it or might have not liked it because it's a new release. And so all this metadata kind of helps us with like the initialization of sending it to like what are most likely the users that would enjoy this. Like, if Drake records a new album or a new song, then everyone who likes Drake is obviously going to probably like this new album, or at least be willing to listen to it.
Yeah. So in reference to cold start, you're going to have very little utilization on your model A, on your collaborative filtering, but a lot more substantial utilization on your model B. But if no one's written any songs about it, and let's say for whatever reason you can't classify it based on, maybe it's a new artist that hasn't launched on Spotify before, then you could, what I want to talk about next is model C of the deep neural network, of actually doing what I'm going to call the hard problem of analyzing the data inside the MP3. And it turns out we have models in order to convert these songs into features, namely, how frequently the BPM is, or I'm sorry, the rate of BPM, or what mood the song is, or the amplitude, or the loudness, or what voices or instruments are used, or what chords are used. And there's an endless list of features, both interpretable and not interpretable. Maybe they're part of hidden layers in your neural network, but you can decompose a song MP3's data into a vector map, and you can convert that vector map into users' tastes, and you'll have to have substantial training data, but eventually you could build a model that will predict a song simply based on the raw data of the MP3 without having collaborative filtering, without having any tags. And I think that could be used as part of your ensemble in order to generate a final product of your Discover Weekly playlist. And actually, one interesting output of this is you can perform math operations of addition and subtraction on combining two songs. If you want to say, hey, I wonder what happens if you combine, I don't know, Nirvana with Eric Clapton. What's the output of that? And then it might output something that will map onto your 2D space a lower dimension space, and perform k-means clustering. And then you get I don't know, Led Zeppelin as your intersection of Nirvana and Eric Clapton.
Got
And you can do things like that in order to perhaps predict what are people going to listen to next. If thing A and thing B are popular, what is the thing C that people will latch onto? You can use that perhaps to drive business decisions. Whereas perhaps in user-user collaborative filtering, I don't think it would be as applicable. And similarly for our tag metadata-based filtering, I think it might be less applicable. Granted, there might be a lot more hidden features in this Model C of a deep neural network, but I think it could be used to drive a lot more, I didn't think of that type answers that could drive business decisions.
Gotcha. Yeah. So it kind of reminds me of like Word2Vec, right? In terms of the what was it like? King plus queen is equal to maybe it's not. No, it was the woman plus king is equal to queen. In terms of that, instead of mapping words to vectors, we are now mapping song MP3 associations to different.
Exactly.
And I
Yeah.
think that's also kind of why you see this kind of new age of like music listening, where Spotify has done a lot of this clustering or word vectorization itself, into actually creating these like new genres that usually no one has really heard of on Spotify,
Exactly.
which is like, you know, like new pop or something, or like chill, chill punk rap or something like that. In terms of that, these are just kind of things that they have now associated with or branded as labels, when they've actually just been clustered into like different like song genres, that no one can really quantify, but you can try to use words to describe what these clusters might be.
Yeah. And I want to mention that because Spotify is as widely used as it is, they have a lot of opportunity to tweak things and say, hey, what if we boost this feature, boost maybe this entire model, and let's see how it drives the bottom line or even an intermediate line, and say, hey, does this give us the results we need? And they can try endless combinations in order to find associations we might not have thought of, and have those things turn into perhaps as classic of a playlist as Rap Caviar. And it's just the experimentation of, essentially at the end of the day, it's experimentation of translating weights and how does that affect our drivers.
Gotcha. Cool. So I guess now that we have this kind of ensemble model, we have this whole architecture for how we might build this generative predictions of different songs, different playlists. How would we actually design this system? How would we scale it? What do we have to think about in terms of the fact that we have like millions of users and millions of songs?
Yeah. Initially, I would really recommend keeping each of these models as a separate service from an engineering standpoint. So we're still resilient if one service goes down, or if we want to iterate on one, we can leave the other one independent. I also very much champion iterative development. So we could start, as I mentioned before, with an MVP of perhaps just model A of collaborative filtering, and gradually introduce new models and gradually extend those weights in order to actually manifest that. One thing that I think is perhaps the most difficult performance question is, how do we perform deep learning across a corpus of, I don't remember how many songs there are, perhaps 300 million, I'll toss out a number. How do we perform deep learning of many hidden layers and feature extraction on terabytes of data, and perform this iteratively and have it function on new songs and have it still be accurate and still represent the new models that data scientists may be coming up with new numbers of layers, new hyperparameters, and so many things changing like that. And I think the biggest win that could be had, at least on Model C, on a deep learning network, is to actually separate that into Model CA and Model CB, where Model CA, all it does is translate an MP3 file into its constituent features, and Model CB takes as input those features and translates those into an output representation of how much a particular user will like a particular song. And my reasoning for that is because both of those are quite difficult problems, but I suspect Model CB will be iterating more frequently than Model CA of translating a MP3 file into its feature map. And my reasoning for that is we're going to have a defined model that will determine danceability or tempo or whatever other features, genre perhaps as a hidden feature of all these songs. And that is going to be fairly static. Yes, we're going to be adding new songs to it, and that matrix is going to be endlessly growing as new artists sign up for Spotify or artists release songs. But at least we have a stable algorithm for generating this output. Then that model B is going to be kind of the opposite side of the coin. It's not going to be extending. It's not going to be growing as often, because whenever an artist releases a new song, it doesn't need to be encoded into model B, but it could be iterating as data scientists are discovering new valuable hyperparameters or new approaches to analyzing this data. So my biggest advice is to separate each component of this ensemble model. And I named 4 components, but there's probably a lot more subcomponents that could perhaps be reused and export the same data in other places. And I think that's going to be a big win in terms of stability and in terms of reducing developer pain and getting their model from their keyboard into reality at 100 million users.
Gotcha. So if I understood that correctly, I think that it's not that each model is dependent upon each other. It's just that each service essentially does one task and then operates independently of each other in terms of being able to generate each kind of task at hand. So like one can do the so-called feature engineering, and then another can do like feature engineering on another part of
Exactly.
the model. Okay, gotcha. And then I guess in terms of data engineering perspective, how would we even begin to store anything such as like the training data? How would we pull that data out? How would we serve this data for online predictions and like the offline batch kind of predictions as well?
Yeah, that problem I'm actually not as scared about. There is the issue of building this collaborative filtering model of how much does this user like this song, because that's kind of on demand as a user listens to a song. And a lot of users is creating a lot of data. And yes, we had optimizations to make it less read heavy or less write heavy in order to just say this value is 1 or 0. And if we wanted to extend that, we could probabilistically increment the write value or the number of listens value, so we could still reduce write ratio. And the other side of this entire problem is doing the batch updates in terms of updating our models and things like that. And I think from a data engineering perspective, keeping things compartmentalized and saying this component has this one job, and if this goes down, it does not affect this other component, I think that'll be a huge win in terms of stability and scalability. In terms of computing, I said 300 million before, but it's probably actually a lot larger. A vector for each of these songs. I'm actually not too scared by that because it can be done incrementally. We can test it out on an initial seed corpus of data. We could say these songs are particularly important and we think they can be used to map onto other songs. These are the artists' showcase songs. These are each top artist's top 10 songs. Let's say we'll index all of those and see how we do, and then incrementally add maybe more songs per artist and more artists with and so now you have more artists with all of their 10 songs. So now you have 2 dimensions, number of artists and number of songs per artist, that you could grow this, and you could see as your curve expands where your weak points are, and you could say, oh, this needs to be scaled here because we can't handle this anymore. But in general, I'm not too afraid of handling even a few billion rows into a single model. I mean, with today's technology, we could reasonably handle that using GPU math calculations to perform these operations in parallel. Thankfully, we can do these operations in parallel because it's largely going to be as new music is added to Spotify's library. I believe that's on Friday or something. So, hey, we want to add a new 1,000,000 songs. Oh, just plug them into our model, generate them in model CA, where we convert an MP3 to its feature map. Okay, add it to scrape all the metadata and add it to model B and compare its usage history onto model A. And now we can incrementally do all these things in batches, and we can see as we, turn the knobs, we can see what things start to break and what things we need to scale up. But I do see this as it's not going to be infinitely scalable, but it will scale pretty high until we need to build a new thing, I suppose, to just have perhaps this entire thing, dare I say, loaded in memory. Of course, it's going to be tested whether it can support that, but I think it's worth a shot, at least in an MVP, to see, can we hold this entire model in memory? Because I suspect yes.
Gotcha. And when you're saying memory with today's technology, I guess, can you go into more specifics on like what that might mean and like what kind of technologies we might use to do so, right? Because if I think about 300 million plus songs, right? Even in a database that's like, I don't even know, like a terabyte plus of just general data, that would be tough to kind of like filter and grab. And so if we load that all into memory, like what would our expectation for like how that might even work, just like in general?
Yeah. So it's less about holding each song's vector in memory, because you could do those in batches. You could do those in sliding windows, like perhaps perform analysis on the first million songs and then the next million songs. I believe it's more about holding in memory all the parameters of your model, which can grow to be billions of terms, but I suspect it would perform all right. And it's billions of terms grows. It still grows. Not exponentially with the number of songs, still grows linearly as you expand your feature map. But it is a consideration, perhaps a weak point of, does this scale infinitely, as our data scientists request new features to be plotted onto this map, or perhaps faster performance. So I would, and all this would manifest itself, to answer your question, and I would suggest cloud compute resources. Those can be scaled up into huge instance sizes. You could even use the various big data management services. I know Google and Amazon have their flagship services, or you could roll your own on just a cloud VM. There's dozens of ways to do it depending on the level that you want to host your own system. I personally have more experience hosting it myself, so I don't have to worry with using their feature toggles. I can dive into the nitty gritty and debug things as they come up. But it's perfectly viable to use a servicified hosted solution. But basically the answer is, I would pay big bucks for the big machines that can handle this compute at a performant time.
Gotcha. Okay. And then in terms of being able to, I guess, serve these Discover Weekly predictions all at the same time on Monday, is there anything that we have to think about in terms of when users want to stream like music all at the same time? Like, how would we serve that kind of music listenability? Like this now, it's kind of less about machine learning and more about kind of like the infrastructure, I think, that goes into users that are listening, like hundreds of millions of users that are maybe listening all at the same time, right?
Yeah. So I don't have too much experience with this, but my estimation would be there would be a single low-level data store that says, hey, this is the corpus for all of our songs. You pass me a song ID, and I will pass you the track information. It will have, the artist, the album, but it will have the MP3 data. Then you'll have load balancers and accessors, workers, but possibly most importantly, I would recommend a caching layer above that. If you're recommending the same new song, if Drake just had a new song drop, a lot of people are going to be listening to it. You're going to want to cache that and not have everything be reading from this low-level data store. And you can have those tiers go up. You can have your caching layer have caching layers. It's very important to have resiliency. So if a caching layer goes down or is temporarily overloaded or unreachable, you can still fall back to perhaps the layer below it, or go all the way down to the root source of truth.
Gotcha.
But I think caching is the answer to this question, and scalability. And as one thing goes down, a perhaps watcher will spin up a new instance and replace it with a new worker.
Gotcha. Okay. I think from my experience too, caching is the solution to almost all problems now. As we expand to this like never-ending field of serving more and more users.
Exactly.
Awesome. Yeah. I guess in terms of just general summary and conclusion, like what do you think about this kind of problem, and then how would you, I guess, tackle it if there wasn't any sort of general framework beforehand? Almost like, I guess, what kind of scale do you think this problem is compared to something like
Mm.
YouTube recommendations or any other kind of problem, basically?
I think it's going to be a lot more domain specific. I think, I don't know, but I think it might be infeasible to take to take every YouTube video and deconstruct it into a feature map based on the video, the data in the MP4 file. I
Hmm.
think it's a lot more feasible because there's a lot less data in songs. And so I think, I don't know, but Model C might be kind of infeasible in the architecture that I described on YouTube as it is feasible on that is more feasible on Spotify. Um, Perhaps relatedly, Model A of collaborative filtering, I think, is similarly strong in both domains, but going to be quite different because you can have as more context. I guess it's kind of blending into Model B. You gain the context of the artist who listens to, or the artist who released this song. Similarly, you do have channels or YouTube content creators,
Hmm.
but I think it's a lot more consistent of a user being a fan of Led Zeppelin and listening to Led Zeppelin's entire discography. And if you've listened to 99 out of 100 Led Zeppelin songs, it's likely you'll like the 100. But perhaps it's less likely that a user on YouTube is going to like every single one of a content creator's resources. They might like this song, this video from this creator, and this video from this other creator. I think there's less YouTube content creator loyalty as compared to artist loyalty. But I might be wrong there. But the joy in this is that through experimentation, we can weight those things differently and say, hey, will we weight the origin of this content as heavily in one context, namely Spotify, as another context like
Hmm.
YouTube?
Gotcha. Yeah, that
So
makes
it's
total
certainly domain specific.
Yeah, definitely. Awesome. All right. I think that was a wrap. Thanks for your help, Dan, and we'll talk to you soon.
Thank you.